So we started off talking about fields, just kind of a generalization of these modern forces, but we've already mentioned Newton's universal gravitational law. And it's not a law. Interestingly enough, this equation doesn't hold true. And Newton even knows it in his time. When he comes up with this equation, we start testing it on some of the things. Well, let me explain. This law, the reason why it's called universal is most people at the time believed that the force of gravity on the Earth was not the same force that kept objects in motion in the heavens. The motion of the planets revolving around the sun is not they believed is not the same force as if I were to drop an apple on near the surface of the Earth. So this invention of this law, this universal gravitational law, says that everything behaves like this. And I think I've already talked about that. I just wanted to reiterate that. But when we start testing it with some of the celestial bodies in our solar system, it turns out that it doesn't work for the planet Mercury. Mercury doesn't quite behave the way we expect it. It's close, but it's not close enough for the purposes of validifying this equation. So it's not a law. It's not a law in Newton's time. It's not a law now. So why is it called a law? Okay. But anyway, a quick rundown. G, universal constant for gravity. M, mass of one object. M, mass of two objects. R squared, the distance from the center of those two objects. So planet, distance in between from the centers of those two objects. Okay, that's R. And then R, remember, is this R hat is direction notation. We're notating which direction R is in this case. Okay, we're saying that this force is in the direction of R, and then we change it with this negative sign, saying it's in the opposite direction of R. Okay, just a little bit of notation there. The other equation that falls into these modern forces, now mind you, they're not modern. Obviously, Newton invented this one, or discovered this one, depending on your point of view. Well, I guess it would be invented because it's not necessarily discovered. Newton invented this one. So it's not modern. I mean, you're talking the birth of physics, boom. We've got this equation floating out of here. The reason why I'm putting it in the modern forces again is because these forces are different than the normal force, than the tension, than what we normally think of gravity, than thrust, than all these other ideas. These are field forces. And it turns out these field forces, are the real forces in the universe. You know, radiating outwards from a point. These fields are really the true forces in the system, or true forces in the universe. So this is one, gravitational. The second one that we're going to cover is electrostatic. Okay, electrostatic is K, Q, Q, R squared, R hat. Remember, R hat is nothing but direction notation. As a matter of fact, you probably will not see that direction notation on any test booklet. Okay, so this is our second law, and it's called Coulomb's law. And Coulomb's law is talking about the interaction between charges. So when we talk about charges, we're talking about properties of protons and electrons. They have a charge. And we know from those properties that electrons repel electrons and protons repel protons. Okay? So we're talking about the interaction between charges. Cool? So Coulomb, meter. Now here's the really interesting thing, and probably one of the most frustrating things I deal with in physics. Coulomb is not a fundamental unit. It's not. Most people still believe it is. I've actually gone on Wikiversity, which is supposed to be considerably better than Wikipedia, and had to make a comment about the fact that somebody had written down Coulomb as a fundamental unit, as a base unit. It's not. An amp is, which is a coulomb per second. And we'll talk about what an amp is when we're going into circuits. But it's not a fundamental unit. This is considered an amp second, or a coulomb. We're just going to call it coulomb for the purposes of this conversation. We're just going to say it's a charge unit. Okay. Now the reason why it's not a fundamental unit is because we didn't really understand what carried charges, what were charges. When Ben Franklin is out there with this kite, with his little key and a jar, he's talking about the motion of charge from one point to another. He's concerned about the ampage, which is that motion. He considers that to be the fundamental unit, the motion of charge. Okay? He doesn't necessarily believe that inside that thread that he's using as his kite string, that there are fundamental charges just sitting there. He only sees the motion of charges, natural phenomenon. He sees lightning. He sees charge move from one point to another. He doesn't necessarily believe, or gets into his head, that these charges exist without motion. Okay, so it's just one of those things that we're stuck with. We'll always be stuck with this, not unless we can. I mean, I guess we can convince the world that Pluto is no longer a planet. Maybe we can start petitioning, international standards to say, hey, look, it's not an amp, it's a coulomb. A coulomb makes sense to me, not an amp. Anyway, another fundamental charge. Look at it. It's the exact same behavior. KQQ over R squared, GMM over R squared. Okay? So we're looking at the exact same behavior between these two. It's another inverse square law. Okay? Here's some really interesting things, though. This force right here, KQQ over R squared, is considerably more stronger than this force. Okay? The force of gravity is at the very bottom on the strength scale. It's way down here. Like it's 10 to the negative 24th in power, while you're looking at, I think, to the 16th here, or I could be wrong. You'll have to check that for yourself. Considerably stronger than this one, but don't we consider probably the gravity the strongest force in the universe? Everything is affected by the force of gravity, right? Well, it's psychological. The reason why we consider this to be a strong force in the universe is because there's no repulsive unit. It's mass and mass. We just have mass. Has anybody played with negative mass? We've played with negative charge. As a matter of fact, we do that all the time. We play with positive charge. We do that all the time. I mean, there's an attraction and a repulsion here. You can achieve a sense of equilibrium between those forces. Okay? Two charges can be forced to stay in a point. Gravitational doesn't necessarily work that way. Gravitational is always pulling, never repelling. Well, never say never, I guess. There is some information out there that's talking about exotic matter that it's leading us to believe that there may be a negative mass value in the universe, but until somebody builds a coffee table out of it, what are we going to do? Which would be really cool. I mean, that's one thing that drives me crazy is people talk about, oh, let's build an anti-gravity machine. You can't overcome gravity. That's like building an anti-electrostatic machine. Nobody builds an anti-electrostatic machine. We just achieve equilibrium by bringing in more charges. Don't build an anti-gravity machine. Build an anti-mass machine. That anti-mass, that negative mass value, would achieve the exact same thing. But I just wanted to quickly talk about these two forces. Anyway, tangent time. So, anyway, we're going to talk about fields, what they look like, and then we're going to talk about potential, and then potential energy, and then we'll be done with modern forces.